Hi, in this video I'm going to solve the problems of the week related to week number 11. You will get a link to the PDF file of the questions that I will going to solve here below this video. And these problems are related to the lecture Algebraic Identities number 3. Okay, so now let us start. Problem A. In problem A, we have given A, B, and C are real numbers. So we know that A and B and C are real numbers. And we know that A plus B plus C is 4. A, B, C is 12. And we also know that 1 over A plus 1 over B plus 1 over C is given to be 1 over 4. Our goal is to calculate a squared plus b squared plus c squared. So this is our question mark in this case, yes? Okay. If you have already watched the video Algebraic Identities number 3, there you see that we had this identity there. So a squared plus b squared plus c squared is a plus b plus c to the 2 minus 2 times ab plus bc plus ca. Okay? So this is my question mark. A plus B plus C is given directly in the problem. I don't have any problem with that. So this part, I need to focus to be able to find the numerical value for this expression. Okay? Okay, so here you see the sum of some fractions. Usually it's better to get rid of fractions. I'm saying usually, not all the time. But of course, in this problem, it's good, yes? So here you see that I have 1 over A, 1 over B, 1 over C, it's 1 over 4. If I want to get rid of all fractions, what should I do? I multiply both sides of this relation by 4 times A, B, C. Yes, so I multiply everything by 4 A, B, C. Then on the left-hand side, we will have this. On the right-hand side, I will have this. Yes, but then let me multiply things inside except 4. Okay, let me keep 4. Of course, you can also multiply 4 inside, doesn't matter, but let us keep it here. So ABC will be multiplied by 1 over A. When I multiply ABC by 1 over A, this A and that A will be cancelled, and I will be left with BC. Okay? And when I multiply ABC by the next term, B and B will be cancelled, and then I will have AC left. And then, if I multiply this by the last term, I will have AB. So at least you see that this is exactly the expression that I am looking for here, yes? What happens on the right-hand side? On the right-hand side, only 4 and 4 will be cancelled, and I will be left with ABC. I would think that you understand what's going on now, yes? Because ABC is also given in the problem. So I can just put 12 here instead of ABC. Then I divide by 4 both sides. Then this becomes 3, yes? So then it means that AB plus BC plus CA is equal to 3, yes? Okay, now if you see the question mark here, this is my question mark, is equal to A plus B plus C is given to be 4, so it becomes 4 to the 2 minus 2 times AB plus BC plus CA, I just got it, it is 3, yes? So it becomes 2 times 3, and this is 16 minus 6, which is 10, yes? So that is the answer to first question. Okay, question number B. We know that A plus B minus C is 1. We are supposed to prove that A squared plus B squared minus C squared is equal to 1 minus 2AB plus 2C. Okay? Okay, one thing you see that I have complete squares here, a squared, b squared, and c squared. It will probably motivate us to raise both sides to power of 2. But there is a problem there. If I raise both sides in this form to power 2, then if you remember about this identity, you will have the first one to the power of 2 plus the second one to the power of 2 plus the third one to the power of 2 plus some extra terms. So it means that what I will get if I just naively raise both sides to power 2 would be a squared plus b squared plus c squared plus some extra terms. Okay? Okay, so in principle, we really don't need to do some trial and error here. We don't need to do that, yes? But we can be a little bit wiser, okay? I want to keep the c squared negative. Okay, so it might motivate you to do this. I would write this in this form. I would write a plus b. I move 1 to the left. I move c to the right. Then I raise both sides to power 2. Then what happens? I will get c squared on the right hand side, but when I move it to the left hand side, it becomes with the negative sign as I demand here, yes? So this is actually easy to see without doing trial and error, okay? Now I raise both sides to power 2. So raising to power 2 strategy was good, but if you naively start raising to power 2 from the beginning, it doesn't work, yes? For the reason that I just mentioned. But hopefully this will work. Let us see what happens. Okay, this is an identity. The first one to the 2 plus the second one to the 2 plus the third one to the 2 plus 2 times the first one times the second one, 2 times the first one times the third one, which becomes negative 2a, and finally 2 times the middle one times the last one, which also becomes negative 2b. And then I will have c squared here. Okay, my goal is to go and reach to this one. You see that I have a squared b squared plus b squared, and I have minus c squared on the left hand side. So it motivates me to move c squared to the left, and whatever is here, I move them to the right. Let us see what happens. So then it becomes a squared plus b squared minus c squared. Okay, this term and that term are moved to the right. They become positive. This becomes negative. And unfortunately, this also becomes negative, but I need a positive one. But you see that I do not have a plus b to a plus 2b here. So we still can do something, yes? What can I do? I can take a 2 out from here. It becomes a plus b. And then I have minus 2ab minus 1. Yes? Now, look here. I can move c to the right now again. It becomes a plus b is equal to 1 plus c. So instead of a plus b here, I can substitute 1 plus c. Yes? So I put this one instead here. So then it becomes what? It becomes 2. Instead of a plus b, I put 1 plus c. And then I have minus 2ab. And then I have minus 1. And if I simplify this, it becomes 2 plus 2c. I multiply 2 inside. Then I have minus 2ab minus 1. But the good point now is that this positive 2 and negative 1 becomes exactly positive 1 that I need on the right-hand side. Then I have minus 2ab. Then I have positive 2c. Now look, I started from here. All these are equal together until I reached here. So it means that under this condition, I was able to prove that a squared plus b squared minus c squared is indeed 1 minus 2ab plus 2c. Okay? Now, let us go to the next problem. Okay. Problem C. A plus b plus c is equal to 0 we are supposed to prove that under this condition, 2 times a to the 4 plus b to the 4 plus c to the 4 is equal to a squared plus b squared plus c squared to the 2. Okay? Okay, so if you remember, we had this identity in lecture 3, algebraic identity lecture 3. So let me write it with box, circle, and triangle. Okay, so we had this box, whatever in box to the power of 2 plus whatever in circle to power 2 plus whatever in triangle to power 2 is equal to box plus circle plus triangle to the 2 minus 2 times box circle plus circle triangle plus triangle and the box. Yes. Okay. Now I want to get something about a to the 4 plus b to the 4 plus c to the 4, which is on the left hand side. Yes. Okay. What I do, I replace this with a squared, I replace circle with b squared, and I replace triangle with c squared. Yes. Okay, so let us plug them here. Then a to the power of 2, another power of 2 will give me a to the power of 4, plus b to the power of 4, plus c to the power of 4, yes? So this is good because I'm getting something related to the sum of the fourth powers. Okay, on the right-hand side, I will have a squared plus b squared plus c squared. Why? Because box is a squared, circle is b squared, and triangle is c squared. And then I have another power of 2 here, minus 2 times, here, box times circle is a squared, b squared. And for the same reason, the next one is b squared, c squared, and finally c squared, a squared. Yes? Okay, so far so good. Let me put this in a box. I would need it. Okay, so let me call it number 1. Okay, so you see, more or less, it's now similar to what I'm going to prove, but the only obstacle for the time being is this term. Okay, I use the same identity here, but I do another thing. I replace something else for box, circle, and triangle. I want to answer this question. So I would replace box with AB. I will replace circle with BC, and I will replace the triangle with CA. Okay, then what happens? The box to the 2 becomes a squared b squared plus circle to the 2 becomes b squared c squared, and then the next one is c squared a squared is equal to. Then the box becomes, the box is AB plus circle is BC, and the other one is CA to the 2 minus 2 times box times circle. Box is AB, circle is BC. When I multiply box by circle, it becomes AB squared C. Yes? And the next one is circle times triangle. Circle times triangle is BC times CA. So it becomes ABC squared. And finally, the other one similarly becomes A squared BC. Okay? Now, I can write it as AB plus BC plus CA to the 2. I hope that you can guess. All these terms share ABC. Yes? So I can factor ABC out. So if I take ABC out, A is left from here, B is left from here, C is left from here. I have written them in an ordered way. Yes? Okay. But you see that A plus B plus C is 0. So this means that this is 0, and then this term will totally vanish. So let me write what I got here. So you see this expression, a squared b squared plus b squared c squared plus c squared a squared is equal in this case ab plus bc plus ca to the 2. Let me put this number 2. Okay. Okay. So you see now the problem is that AB plus BC plus CA is not known. But that is not an obstacle. Let me start from here again. I have A plus B plus C is equal to 0. Let me raise both sides to power 2. Yes, this becomes A plus B plus C to the 2. It becomes 0 to the 2. Yes, but then you know what can I write instead of this expression? I can write A squared plus B squared C squared 2 times AB plus BC plus CA is equal to 0. Yes. My goal is to find AB plus BC plus CA, so I move everything to the right-hand side. All of them becomes negative. I factor the negative sign out, so it becomes 2 times AB plus BC plus CA is minus A squared plus B squared plus C squared. And then I divide everything by 2, so then finally I get this relation. Yes. Yeah, it's a little bit complicated. I probably should have assumed this to be a little bit challenging, not the other one probably. Okay. Now C. This is number 3. So AB plus BC plus CA is this expression. I can put that expression here. Yes. Yes. So you see that comparing 1 and 3, what can I conclude? A squared plus B squared, comparing 2 and 3. A squared plus B squared, A squared B squared plus B squared C squared plus C squared A squared is equal to AB plus BC plus CA to the power of 2. Yes? But AB plus BC plus CA is this expression. So then it becomes minus a half A squared plus B squared plus C squared to the power of 2. Yes? So then it means that this is equal. If I raise it to power 2, it becomes 1 over 4. Then I have A squared plus B squared plus C squared to the power of 2. Yes? Now everything is more or less finished. Now let us go to number 1. So from number 1, so this implies that instead of A squared plus B squared plus C, instead of this expression, A squared B squared plus B squared C squared plus C squared A squared in this relation, I can substitute this expression. Yes, so what happens? It becomes A to the 4 plus B to the 4 plus C to the 4 is equal to A squared plus B squared plus C squared to the 2 minus 2 times this expression. But this expression is equal to that. So it becomes 1 over 4 A squared plus B squared plus C squared to the 2. And then you see that the relation that you want to show, we have a 2 here. So it motivates us to multiply both sides by a 2. So then it becomes 2A to the 4 plus B to the 4 plus C to the 4 is equal to. This will be multiplied by a factor of 2. Yes? 2 times 1 over 4 is a half. and I am supposed to multiply everything by 2, that 2 will cancel this 1/2, and what is left is a to the 2 plus b to the 2 plus c to the 2 to the 2. But you see, I have 2 of these expressions minus 1 more of that same expression. So 2 times something minus one of those things, it becomes exactly one of those things, yes? One of those numbers. So it becomes a squared plus b squared plus c squared to the 2. And now if you look at here and the final term, you immediately realize that we actually succeeded in proving this. Okay? Now let us go to the next problem. The next problem is that part D. So A, B, C, X, and Y, and Z are non-zero real numbers. Okay? And we have A plus B plus C is equal to 1. A squared plus B squared plus C squared is also 1. And we know that X over A is Y over B is Z over C. Then we want to show that under all these conditions, X times Y plus Y times Z plus Z times X is 0. Yes? Okay, I don't know, I call this challenging because probably it needs a little bit of trick. So usually if you have these kinds of expressions, 3 fractions equal together, one thing that can help you is to give these numbers a common name. Because you say that they are equal, so I can call them equal to some number. For example, in this case, I would call it t. So I would say let these common numbers, they are the same. So I call all of them to be t. Okay? So then what can I get? I can get that if I consider this one with the last one, I have x over a is equal to t, but t can be written as t over 1. Then I use the cross product rule. So then it means that x is equal to a times t. Okay, so similarly, I can conclude that x is equal to at, as I did here, and y is equal to bt for the same reason, and z is equal to ct. Yes? Okay. By the way, we are supposed to prove that xy plus yz plus zx is 0. Okay, so let me calculate this expression to see what is the how can I find the relation for xy plus yz plus zx. Okay, therefore this implies that xy plus yz plus zx is equal to, I still don't know it is 0, but I am simplifying my expressions using these terms here. So x times y, what happens? X is this one, y is this one. So if I multiply them, it becomes abt squared plus. Then I have y times z. So this one multiplied by that one, it's bc, and then I have t squared, and then finally I have z times x, which is ca, again t squared. Yes? Okay. So what can I get? I can factor t squared out. Then I will have ab plus bc plus ca t squared. Okay? Now I think it is very, very clear what's going on, yes? So you see, I want to prove that this expression is 0. Using this trick, which is common, very, very common, if you have fractions equal to them, one possible trick is to give them a common name and try to see how are they related somehow. Okay, so here I did this trick, which I knew very well, and then I wrote xy plus yz plus zx in terms of that t. Yes, I got this one. Now look back. I have this expression and I have that expression. Can I get any information regarding this expression? Yes, yes, it's the famous identity. Yes, so what can I do? I can write that a plus, so from here, it becomes a plus b plus c to the 2 is also 1 to the 2. I raise both sides to the power 2. Then the left-hand side is this identity that we learned in lecture 3. So this is a squared plus b squared plus c squared plus 2 times ab plus bc plus ca. And the right-hand side, 1 to the 2, is also 1. But then look, a plus b plus c is given to be 1. So, okay, I use that fact. A squared plus b squared plus c squared is also equal to 1. So this expression is 1. Okay? 1 plus something is equal to 1. So it means that this expression is 0. So this implies that 2 times AB plus BC plus CA is 0. But this in turn means that AB plus BC plus CA is 0. Okay? And now the expression that I was trying to prove that this is 0 is equal to this expression times some number t. Of course, t squared, I don't know what t is, but it doesn't matter because this expression is 0. And if you put it here, then this becomes, so if I put 0 here, it becomes 0 to t squared, which is of course 0. And that is what I am trying to show. Okay, so let us go to the next problem. Okay. E. X is a real number such that x squared minus 3x plus 1 is equal to 0. You are supposed to find the exact value of these expressions. Of course, one naive way of solving this problem is solve this quadratic form equation using PQ or ABC formula and find the numbers. But you can try it yourself. The numbers contain a square root sign, and the calculations would be very messy if you want to raise those numbers to power 2, to power 3, to power 6 and add them together. So even though in principle this strategy will work, but this is not what I want to adopt here. Okay? Okay. Another way of thinking is all these expressions somehow are related to a combination of x plus its reciprocal 1 over x. But the expression given is not in that form. It might motivate you to divide both sides of this expression by x. Yes? But can I divide both sides of equality by any x? Yes, except one exception, and that is when x is equal to 0. But it is completely clear that x cannot be equal to 0. Why? Because if x is 0, this term becomes 0, this term becomes 0, and then this becomes 1 equal to 0, which is a contradiction, yes? So it means that I am on the safe side. I am completely sure that my x is not 0, so I can safely divide both sides by x, yes? Okay, but there are 3 terms to divide by x. X squared divided by x is just simply x. Minus 3x divided by x is just simply 3. And the other one is 1 over x. And on the right-hand side, 0 divided by x is 0. So now you see that why this was good if I divide both sides by x. Okay, then it means that x plus 1 over x is 3. Yes? I moved 3 to the right-hand side. Okay, and then do you remember from, I think it was lecture 1, we had this relation. Yes? So if I replace the box with x, and if I replace the circle with 1 over x, then this becomes x squared. The other one becomes 1 over x squared. But on the right-hand side, I will have x plus 1 over x to the 2, minus 2 times this, the box times the circle. But box is x, circle is 1 over x, so if I multiply them, it becomes 1. And then I have a 2, so this becomes just 2. Yes? But I realize that x plus 1 over x is 3, so if I plug 3 here, so it becomes 3 to the 2 minus 2, so it becomes 9 minus 2, it is 7. So the answer to this part is 7. Okay? Okay. And in algebraic identities lecture 3, I just showed this identity to you, that this to 3, this 1 to the 3 is equal to yes. So if you go and watch the video, you will see that there we discussed about this identity and solved some problems related to that. Now here I substitute the box with x and I substitute the circle with 1 over x. Okay, because now my goal is to calculate the sum of cubes. Yes. Okay, so then it becomes x to the 3 plus 1 over x to the 3, box to the 3, circle to the 3 is equal to box plus circle to the 3 minus 3 times box times circle. Again, box times circle is 1. X times 1 over x is 1. So this is 1. I don't, if you want, let us write it here. And then I have again box plus circle. So it's x plus 1 over x. So this is my question mark is equal to x plus 1 over x. We just got it from the information provided in the problem. It's 3 to the power of 3 minus 3 times 1 times this one is again 3. So it is 27 minus 9, which is 18. Okay, now for calculating x6, x to the 6 plus 1 over x to the 6, or we can do it in two different ways. We can replace the box by x squared and circle by 1 over x to the power of 2 here in this equation. Or I can replace the box and the circle here by x to the 3 and 1x to the 3. So let me do one of them. You can do the other one yourself. Yes. So here, let me replace the box with x to the 3, and let me replace the circle with 1 over x to the 3. So then box to the 2 becomes x to the power of 6 plus circle to the 2 is 1 over x to the 6. That is exactly what I want to calculate. That's the question mark. This is equal to box plus circle to the 2. So this becomes x to the 3 plus 1x to the 3 to the 2 minus 2 times box times the circle. Still box times the circle is 1. X to the 3 and 1x to the 3 are the reciprocal of each other. So the product is 1. So this is just simply this. And we just right now calculated, you see, x to the 3 plus 1x to the 3 was 18. So I can put 18 here to the 2 minus 2. And then this is 324, 18 to the 2 minus 2. So it is 322. Yes? Okay. Let us now go to the next problem. In the next problem, to save time, let me not clean these two. Might be I will need them. So let me clean this part. Okay. So let me write the question for you first. The question asks you that, okay, we know that this is question F. We know that a squared plus b squared is equal to 1. We are supposed to show that 2a to the 6 plus b to the 6 is equal, minus 3 times a to the 4 plus b to the 4 is equal to, no, we want to find this. We want to find the exact value of this expression. Okay, so let me use this identity again for this part. Okay, so here I replace box with a squared and I replace circle with b squared. Okay, I plug them here. Box to the 2 becomes a to the 4. Circle to the 2 becomes b to the 4. And then what I get is I get a squared plus b squared, because box is a squared and circle is b squared to the 2, minus 2 times a squared b squared. Okay, so this implies that a to the 4 plus b to the 4 is equal to a squared plus b squared is given to be 1. So 1 to the 2 is 1. So I can write 1 minus 2a squared b squared. I cannot go further. I don't know. I don't have any information regarding the product of a and b. So I have to keep it. But then let us go back here. So let us clean the extra pieces. I don't need them. I need this identity once more. Okay, so I can clean this one as well. Here, you can see that, yes, for this identity, to produce 8, 6 plus b6, I replace b here. I replace the box with a to the 3 and the circle with b to the 3. Yes, so if I plug them here, no, sorry, again to the 2. Okay, because I am supposed to calculate a6 plus b6. If I put them here, the first one becomes a to the 6. The second one becomes b to the 6. And on the right-hand side, I will have a squared plus b squared to the 3, this one, minus 3 times a squared b squared multiplied by the box plus the circle. But the box is a squared and the circle is b squared. And then look back again. A squared plus b squared is 1. So this expression is 1 to the 3. This is 1. 1 to the 3 is 1 minus a squared b squared we don't know. So we have to copy and paste it again. But a squared plus b squared is again 1. Okay, so you got that. Okay, but what is my question mark? The question mark is 2 times a6 plus b6 minus 3a to the 4 plus b to the 4. But a to the 6 plus b to the 6 is that expression. So I would write 2 multiplied by 1 minus 3a squared b squared. And then I have minus 3 times a to the 4 plus b to the 4. And that is that expression. Okay, let us see what happens if I multiply things. So it becomes 2 minus 6a squared b squared minus 3. I multiply minus 3 inside. So then it becomes 6a, positive 6a squared b squared. So you see, I don't need the product. Why? Because this is canceled out. And then 2 minus 3 is minus 1. So the answer to this question mark is minus 1. Okay. So problem G. In problem G, we know that a and b are positive real numbers. They are positive, and of course, I know that according to the problem that a is greater than b. And we also know that a squared plus b squared is 3 times ab. We are supposed to determine the exact value of this expression. A to the 3, b to the 3 divided by a to the 3 minus b to the 3. This is wanted. Okay, so if you remember what I said in lecture number 3, algebraic identities 3, we have two identities for a to the power of 3 plus b to the power of 3 and a to the power of 3 minus b to the power of 3 in the factorized form. Okay, so I would write them. For the numerator, I can write a plus b, a squared minus ab plus b squared, and then I have, for the denominator, I have this expression. Okay? Okay, so let us see what happens. Here I have a good combination a squared plus b squared, which is given to me 3ab. And I have the same expression a squared plus b squared here. So, okay, of course I don't know what to do for them right now, but let us copy and paste them. But instead of a squared plus b squared, I put 3ab, but I have a negative ab here. 3ab, negative ab becomes just 2ab. Yes? And then I would copy and paste a minus b parts, but again, a squared plus b squared is 3ab, but I have an extra positive ab here, so it becomes 4ab. Okay, but you see that this expression 2 and a and b are all factors of the numerator. They are also the same, they are factors for the denominator. So this a and this b and this a and that b are simplified. And then I have a 2, which will be simplified by 2 of them, 2 is left. So the question mark is now simpler. It's only a plus b which is left in the numerator, and this is 2 times a minus b in the denominator. So let me write implies that the question mark is equal to that. Okay? Now I need to find a plus b and a minus b. Okay, so I have a squared plus b squared is equal to 3ab. I add 2ab to both sides. Then this becomes a squared plus b squared plus 2ab. And on the right-hand side, 2ab plus 3ab becomes 5ab. Yes? Okay, so why this is good? So then this becomes the a plus b to the 2 is equal to 5ab. Yes? So then it means that, so you see a and b are said to be positive and a is greater than b. So everything is positive. So I take a square root from both sides. Then it becomes square root of 5ab. Yes? Of course, in principle, I should put plus and minus. But a and b are positive numbers, so a plus b cannot be a negative number. This is why I didn't put the negative sign. I didn't consider the negative sign. And I hope that you understand what to do for a minus b. Instead of adding 2ab to both sides, I subtract 2ab from both sides. Then it becomes a squared plus b squared minus 2ab. On the right-hand side, I had 3ab. I subtracted 2ab from it, so only ab is left. And then this time, this becomes a minus b to the 2 is equal to ab. Okay, so it means that I have a minus b is equal to square root of ab. Why? In principle, again, I should write either positive or negative, but this condition is given for this. A is greater than b, so it means that a minus b is a positive number, so I am not allowed to put the negative sign there. So that is the only thing that is given. Okay, so now if I substitute these two, so if I substitute these two in my question mark, so the question mark is now equal to, it's a plus b, so I put square root of 5ab, and then I have a 2 here, and then instead of a minus b, I can put the square root of ab. But this can be written as a square root of 5, square root of a, square root of b. This can be written as 2 square root of a, square root of b, the product. This and that cancel, so what is left is just the square root of 5 divided by 2. Okay? And finally, let us solve problem H. So x and y are real numbers. We know that x minus y to the 3 is equal to 4. And then x minus y is equal to 1, and I am supposed to calculate this. Okay, again, that is also simple. So I use the same identity that I use for the denominator here. I can factorize it in this form. Is 4. But x minus 1 here is given to be 1. So 1 times this expression is the same expression. And if you don't mind, let me write x squared plus y squared next to each other. And then I have plus xy equals to 4. Okay, so that's one expression. Okay. Now here, if you raise both sides to power 2, then it becomes x minus 1 to the 2 is 1. But this becomes the quadratic pattern. This becomes x squared plus y squared minus 2xy is equal to 1. Yes? Okay. So because my question mark is x squared plus y squared, let me multiply this by 2. It becomes 2x squared plus y squared. Then I will have 2xy equals to 8. Yes? And I can write this below here. It is x squared plus y squared minus 2x squared is equal to 1. If I add these two expressions, 2x squared plus y squared plus one of them becomes 3x squared plus y squared. And this one and that one are canceled. 1 plus 8 is 9. So now my question mark is this, so I divide everything by 3. So then it means that x squared plus y squared is actually 3. Yes? Okay. So thank you for watching the video. I hope that these videos are useful for students. Okay. If you have any comments, suggestions, objections, I would be very happy to hear them from you as a comment below the video. Thank you.